we will now continue with two more examples of double integrals that are best evaluated using polar coordinates. So we want to find the volume of the solid that lies under the paraboloid z equals x squared plus y squared, above the xy plane, and inside the cylinder x squared plus y squared equals 2x. So the domain that we want to integrate over is this cylinder x squared plus y squared equals 2x. And it might not be immediately apparent that that's a cylinder. We might want to rewrite this as x squared minus 2x plus y squared equals 0. But I'm going to complete the square, so I'm going to add 1 to both sides. And so I can rewrite this as x minus 1 squared plus y squared is equal to 1. And so now you can see the equation of a circle. The center of that circle is 1, 0, and then the radius of that circle is 1. So here I'm going to draw that circle whose radius is 1 and who's centered at 1, 0. Okay, now because I have a circle that represents my domain in the xy plane, we can understand that in cylindrical coordinates that actually represents a cylinder because z can be anything. But now I want to describe that domain. It is a circular domain, and so I think it'll be best described in polar coordinates. So I'll recall that x squared plus y squared is equal to r squared, and that x is r cosine theta. So I can rewrite this as r squared equals 2r cosine theta. Now if I divide by r, this will just be r equals 2 cosine theta. And so now I've described this domain as r being a function of theta. Okay, so if I want to find the volume, I am going to write this as a double integral. And that's a double integral over the cylinder, x squared plus y squared equals 2x. So I'm just writing the domain underneath the double integral there. And I'm trying to integrate under the paraboloid x squared plus y squared. And I can integrate that, say, dy dx. And then I want to describe it in polar coordinates. So here, x squared plus y squared is equal to r squared. dy dx is equal to r dr d theta. And then I've got to think about, well, what is the range of the radius? Well, the radius, as you can see, is as small as 0 because the point 0, 0 is included, and as large as the circle that I've drawn, which is defined by 2 cosine theta. So that's the range of the radius. But now you have to ask yourself, well, what is the range of the angles? Well, let's first think about if I have r equals 2 cosine theta. If theta is 0, then I get r equals 2 cosine 0, or r equals 2. So when the radius is 2, that's actually when theta here is 0. And then if I let theta be something like pi over 4, then I get that r is equal to 2 times cosine of pi over 4, or square root of 2. So if I draw this out here, I'm going to draw where theta here is pi over 4. Then this point here corresponds to theta being pi over 4. And the radius there, as you can see, because the height here is 1, that the radius there will be the square root of 2, which is what you'd get when theta is pi over 4. Now, if I let theta be pi over 2, then cosine of pi over 2 is 0. So r is equal to 2 times 0. So theta equals pi over 2 is here. Okay, so I can see that the range of theta is going from 0 to pi over 2, gives me the top half of the circle. What's the best way to describe the bottom half? Well, I'm going to do this in reverse. This is actually here, theta equals minus pi over 4. And if you go back to 0, then you can also that's also equivalently theta equals minus pi over 2. And so I can write theta as being from minus pi over 2. Okay, then I'm going to essentially trace down from minus pi over 2 through to 0 and then around to pi over 2. So it goes from minus pi over 2 to pi over 2 for theta. So I've now converted this to a much simpler integral in polar coordinates, and now all I have to do is evaluate that integral. Okay. Well, let's continue this along. So we're going to say that the volume is equal to the integral from minus pi over 2 to pi over 2. I can't separate out the two integrals. I realize that the function only depends on r, okay? But this limit here depends on theta. So I can't separate out the integrals like I have done in the past. So I'm going to need to just find the antiderivative of r cubed there, which is 1/4 times r to the 4th. And I want to evaluate that between 0 and 2 cosine theta. And I'm still going to need to integrate the result d theta. Okay, so this becomes the integral from minus pi over 2 to pi over 2. And 1/4 r to the 4th. So 2 to the 4th is 16. So 16 divided by 4 is 4. So I'm going to get 4 cosine to the 4th theta d theta. Okay, so something else that I want to do here is I have the integral of an even function from minus pi over 2 to pi over 2. I'm going to simplify this and do twice the integral from 0 to pi over 2. And I'm still integrating 4 cosine to the 4th theta. I'm going to write this as 2 cosine theta, 2 cosine squared theta, squared d theta. Now, I've got 2 times the integral from 0 to pi over 2. And 2 cosine squared theta, well, there is a trig identity for 2 cosine squared theta. That's actually equal to 1 plus cosine 2 theta. And that'll need to be squared d theta. Okay, so you have to think back to when you had to integrate even powers of sine and cosine. You would use an identity that said that 2 cosine squared theta is equal to 1 plus cosine 2 theta. Now, I just need to expand that out. So this is 2 times the integral from 0 to pi over 2 of 1 plus 2 cosine 2 theta plus cosine squared 2 theta d theta. Okay. So let's continue along. I'm going to start doing some of these antiderivatives. So I'm going to get 2 times, okay, antiderivative 1 is theta. The antiderivative of cosine of 2 cosine 2 theta is just a sine 2 theta. And I'm going to evaluate those between 0 and pi over 2. And then I'm going to add the integral from 0 to pi over 2 of, and then I'm going to do the same trick I had before. I have a 2 cosine squared 2 theta. So that is going to be a 1 plus cosine, 1 plus cosine 4 theta d theta. Okay. So what's left? Let's see. I have 2 times theta. So I have 2 times theta is pi over 2. Sine of pi is 0. And then when I plug in 0 for theta, I get 0. When I plug in 0 into the sine 2 theta, I get 0. So I get 2 times pi over 2. Okay, plus, now taking the antiderivative of 1 there, I'm going to get a theta. Okay, and then this becomes minus 1/4 sine of 4 theta evaluated between 0 and pi over 2. And so I'm going to get, let's see, pi plus pi over 2. And then when I plug in pi over 2 to sine 4 theta, I get sine of 2 pi, so that's 0. And then when I plug in zeros, I get 0. Okay, so in fact, I'm going to get 3 pi over 2. Okay, so the volume, okay, within that cylinder, underneath the paraboloid x squared plus y squared is going to be 3 pi over 2. Okay, let's look at one final example of finding a volume. In this case, we want to find the volume of the solid that is bounded above by z equals 8 minus x squared minus y squared, and that's a paraboloid facing down, and then below by the paraboloid z equals x squared plus y squared. So we're finding the volume between 2 paraboloids. Okay, that first paraboloid is z equals 8 minus x squared minus y squared. Okay, it's opening downward. And then the second paraboloid is going to be z equals x squared plus y squared. Okay, and that's opening upward. And we're trying to find the volume between these 2 paraboloids, making this sort of egg shape. So in order to do this, I need to find where the paraboloids intersect so I can find the boundary of where we need to integrate. So if I want to find the intersection, okay, they're both defined by z equals, so I'm going to set them equal to each other. Okay, so we're going to set, let's set x squared plus y squared equal to 8 minus x squared minus y squared. So that's going to tell me that if I add x squared plus y squared, okay, then I'm going to get 2x squared plus 2y squared is equal to 8. If I divide by 2, that tells me x squared plus y squared is equal to 4. Okay, so the intersection here is a circle, and that is the circle x squared plus y squared is equal to 4. So what I really want to do is I want to integrate over this domain right here where x squared plus y squared is less than or equal to 4. So let's find the volume here. Okay, the volume between 2 paraboloids should be an integral over that circle x squared plus y squared less than or equal to 4. Okay, and then the upper surface is 8 minus x squared minus y squared. So we want to get the volume underneath that paraboloid minus the volume underneath the opening up paraboloid x squared plus y squared. And then this is again over a circular region. I see lots of x squareds plus y squareds around that tell me polar coordinates is the best way to go. So I'm going to describe the circle in polar coordinates. It's from radius 0 to 2, because that's the radius of our circle. And then the angle is from 0 to 2 pi. I'm going to integrate 8 minus r squared minus r squared. And that's going to be times r dr d theta. Okay, that's substituting in for the dx dy. Now, in this case, my function just depends on r, nothing else. So I'm going to separate out the theta integral. So it's the integral from 0 to 2 pi d theta. Okay, and then I'm going to integrate from 0 to 2, and this will be 8r minus 2r cubed dr. So this becomes, let's see, the integral from 0 to 2 pi of d theta is going to be 2 pi. And then the antiderivative of 8r is going to be 4r squared, minus the antiderivative of 2r cubed is going to be 1/2 r to the 4th, evaluated between 0 and 2. So I'm going to get 2 pi times, let's see, 4r squared. So 4 times 2 squared is going to be 16, minus 1/2 times 2 to the 4th. Okay, that's going to be 1/2 times 16, or 8. So 16 minus 8 is 8, and 8 times 2 pi gives me 16 pi. Okay, so the volume between these two paraboloids is going to be 16 pi.